All right, the next thing to consider is not just how high the waves are or how frequently they occur, but isn't there changes in the spacing? So if I look, the space between, let's just pick a spot. A convenient spot typically is the peak to a peak. And the wavelength is the distance between one peak to another, and this is called, abbreviated with the Greek letter lambda. So lambda is associated with the wavelength itself. All right, now, I've gone boating, for example, in the Delaware Bay, and several years back, there was a boating accident. This freak storm came out of nowhere, and the waves got very, very choppy very quick. The problem with that was the waves became so frequent and the spacing was so tight, people's boats could not recover from the waves, and they were tossed around, and people were actually killed in that particular storm. So we're not only concerned about how tall the waves are, very important, not only how frequently they arrive, but also how far apart they are, what is the spacing of those waves. All right, now, there are other types of waves. So what I'm going to draw over on this side is an alternative to this. So let's just pretend we have a slinky, and the slinky itself has spaces in it. And what I'm going to do is push on the slinky and give it a little bit of a compression. And the wave kind of looks like this. Picture the slinky. Now, if I push on a slinky, instead of going side to side like a snake, I'm going to take one end of the slinky and then I'm going to push on it. And boy, this is a big slinky. All right? If I push on it, we can actually see a pulse travel through the slinky itself. I'll set it on a tabletop. I'm not sure if you're going to be able to see it well. We'll probably do this in class. But if I push on it, you can actually see the pulse travel through the slinky itself. This is called a longitudinal wave, also known as a compression wave. So longitudinal wave is going to be a compression wave. Longitudinal. Also known as a compressional wave. Now, when we look at the wave itself, certain areas are spaced apart, and then when they're combined together, very close together, that's where the wave pulse. This is the compression. And then here we have an expansion, also known as a rarefaction. So the wave, as it travels through, this pulse, this compression, will actually travel its way through, and then they're coming out on the end. This type of wave is associated with sound waves. So when I speak it, I say, hey, pay attention. What's actually coming out of my mouth is a pulse, a change in the pressure. So that sends that pulse out to your eardrum. So when I say, hey, hey, it sends a pulse out, travels through the air, and then when it reaches your ear, the pulse goes back and forth and then moves your eardrum in and out like so. Now, the question is, does the actual air from my mouth go into your ear? And the answer is no. Just like when I hold the slinky out, this end of the slinky never actually touches this end of the slinky. The pulse travels through the slinky itself, but the ends of the slinky don't actually change. So the air from my mouth sets up a pulse through the air, which pushes on the air molecules, which push on the next set of air molecules, which push on the next set of air molecules. Eventually it reaches your ear, and then those air molecules that were right outside your ear actually make that vibration, making your eardrum move back. And then you go, oh, I heard you, Mr. Hessler. I'll try to behave myself from now on. So just picture, all around the room, when I send out this pulse, here, this direction, this direction, this direction, basically as I say or speak, hey, the pulses go out in very many directions. So think of it as a whole bunch of slinkies coming out of my mouth and going into all the eardrums. As a matter of fact, there's so many of them, we could actually think of it as a sphere that's expanding outward, creating this wave pulse as it goes forward. This is associated with the sound wave. This is called a longitudinal wave. The wavelength and the peaks are measured between the expansions and the compressions. The wavelength would be from, say, one compression to the next, something along those lines. So the compressions are kind of like the peaks on this one, and the parts that are expanded are kind of like the troughs. So there's a nice analogy for those.